Welcome everyone to the fourth Sysrev user webinar, where we will be listening to a presentation by Dr. J.J. Duke and Dr. Troy Cross on the methodological quality of the work of breathing during exercise, a systematic review. Real quickly, Dr. J.J. Duke is an associate professor at the Northern Arizona University in Flagstaff, Arizona. He studies the integrative physiological response to exercise and the environment, with a focus on respiratory mechanics in healthy individuals and adults born preterm. Troy Cross is a senior lecturer at the University of Sydney in Sydney, Australia. His research focuses primarily on the energetics and mechanics of breathing during exercise in health and disease. I really should just let people introduce themselves. Please take it away. Thank you.
Thanks, TJ, for the introduction, and thank you to everyone for attending the webinar today. As TJ mentioned, we're going to talk to you a bit about our systematic review involving the work of breathing during exercise in adult human beings. Of course, we're your speakers. I'm JJ, and Troy, and I'm going to start us off, and Troy's going to wrap up in the second half. No need to introduce ourselves again after TJ has already talked so highly of us. I'm going to introduce or remind us of how to measure work. Those of us not physics inclined may benefit from a slight brief reintroduction to the concept. I'll also talk about the work of breathing, how we would measure it, what little tools do we need to measure the work of breathing, and why would we even care about measuring the work of breathing during exercise. And then I'll finally conclude with why we're going to talk about, or why we would be interested in conducting a systematic review on this topic. Troy is then going to take over and talk about the workflow within Sysrev itself, as well as talk about the information we hope to glean from the literature and provide us with the current results, and then provide a summary of the results and conclude and wrap things up. So first, let's just remind ourselves of what is work. In the classic one-dimensional sense, in the linear sense, work is simply defined as force times displacement. So we push or force a mass over a given distance, and then the multiple or integral of that ends up as Newton meters or joules. When we start to look into the work of breathing, we are then going to be applying a pressure through a given volume. In the two-dimensional situation, we would be integrating pressure over a given volume. Pressure is just another way of saying force applied over an area. And we then apply that force on this surface and effectively move the object, as Troy's moved for me. This would then move the object, in our case, the lungs, the chest wall, or the entire respiratory system in three-dimensional space, some volume. We then would integrate pressure over the volume, and ultimately the units will result in joules, which is our classic unit of work. On to the next one, Troy. So the work of breathing is simply defined as the respiratory muscle pressure generated over some volume. We typically can think of this as an energetic cost to move air into and out of the lungs. In order to quantify the work of breathing, of course, we're going to need a pressure and we're going to need a volume. The pressure in question here is the pleural pressure. Pleural pressure is the pressure inside of the very small space in between the lungs and the rib cage. It is incredibly invasive and dangerous to directly measure pleural pressure. They don't even do this in animals. And so we definitely do not do it in human beings. Rather, we measure a correlate of pleural pressure, which is esophageal pressure. To measure esophageal pressure, we are going to need a device that is capable of measuring pressure inside of the esophagus. There's multiple types of devices that can be used for this purpose. Essentially, it's a catheter that gets passed through the nose. The participant swallows it. It's passed down to the lower, quote unquote, lower third of the esophagus, sitting just above the diaphragm. And that is how we would quantify esophageal pressure. The volume in question here is going to be the volume of breath during an inspiration and the volume of breath during expiration. And finally, we're going to take this esophageal pressure and volume data and create an a pressure volume loop, as is depicted on the screen here. And then we simply take the area of that irregularly shaped oval, and that provides us with a measure of work in joules. This would be the work for a single breath. So the work of one single breath. Again, we do, if you go back, Troy, sorry. if we just to keep in mind a couple of things. Again, we have that catheter capable of measuring esophageal pressure. That needs to be accurate. It also needs to be able to transmit those pressure changes quickly enough so that we're measuring things kind of in phase at the same time as all of our other measurements. So when we're talking about a dynamic situation like exercise where pressure swings can happen 60, 70 times per minute, the device really has to have a high dynamic response. The device that catheter is going to be connected to, our pressure transducer, also needs to be accurate. It also needs to be calibrated prior to use. And the device that's going to measure our volume, which we typically measure airflow or the rate of air coming into and out of the mouth. We then integrate airflow over time and we get volume. That device also needs to be accurate and also needs to be calibrated prior to each use. These are some of the attributes from the literature that we kind of wanted to learn a bit about. What's there, what are people saying, what are people doing? Now time to visit your friend Troy on the next slide. So I've been talking about the work of breathing. So again, that's just the work for that one single breath. It's also really common to depict or articulate the work over a given period of time. So the work per minute, if you will. The work per minute is technically defined as the power. The units do correspond to units of power in joules per minute. In order to get the power of breathing, I would simply multiply my work for my one breath times the number of breaths per minute, and I would end up with joules per minute. There's been a tendency in the literature for researchers to depict or report the work of breathing in units of power. Work and power are not the same physiological parameter and should not be considered as so. And so the frequency with which this occurred was something of high interest to us for our systematic review. Go ahead and go to the next slide, Troy. So the work of breathing, again, we have this parameter. We've talked about how we would compute it, the devices that we would need to compute it. The work of breathing is related to exercise in that as ventilation changes, or the rate of breathing, the volume of air being moved per unit of time, or ventilation. As ventilation increases, so does the work of breathing. This is a figure from a publication that we had earlier this year relating the work of breathing on the y-axis, as Troy was just moving the cursor, to minute ventilation. You could see the roughly curvilinear relationship between the work of breathing and minute ventilation. And this hopefully will make intuitive sense such that if I'm only moving 10 liters per minute of air, it's going to cost me some arbitrary value, some number of joules. If I then start to breathe 100 liters a minute, of course, that's a tenfold increase in the amount of air I have to move, and therefore there's going to be a compensatory increase in the amount of work. So why would we even care about this work of breathing? The work of breathing does provide a substantive amount of information in regards to the mechanics or energetics of the respiratory system. I typically teach this concept to my students as the how of ventilation. The mechanics are how we actually can get air to flow into and out of the lungs. In brief, we have to contract respiratory muscles. The contraction of that muscles have to be in excess, the pressure to contract those muscles or generated by those contracting muscles have to be enough to overcome the respiratory system, the weight of the respiratory system, the tendency for there to be resistance as air moves through the airways. This provides a lot of information about those attributes of the respiratory system. And depending upon the method used, which I'm going to get into here in a couple minutes, we can learn a varying amount of information about the respiratory system. We also know that the respiratory muscle work, or the work of breathing, changes with a variety of clinical situations. Lung disease, heart disease, all make the work of breathing in excess to what is needed for a healthy individual. And this has some downstream effects on the individual's ability to exercise, their sensation of breathlessness, so how out of breath they feel, which ultimately determines how long they can exercise, or how much exercise they can ultimately tolerate. So you can go to the next slide, Troy. The means by which I have been describing the calculation or computation of the work of breathing is by far the simplest means by which we could do this. I've been describing what we call pressure volume, or PV integration, which Troy is highlighting with his cursor. That provides the least amount of information, but it is by far the simplest way to compute the work of breathing. All we are doing is simply calculating the area of an irregularly shaped oval. There are 4 common methods used in the literature. They range in complexity, starting with PV integration, the simplest. You need the fewest number of tools in order to make that measurement. On the other end of that spectrum is the Campbell diagram. The Campbell diagram requires the most number of inputs, so we've got to make some measurements prior to starting exercise, and we also have to have some breathing maneuvers during exercise to allow us to assemble a Campbell diagram and compute the work of breathing via a Campbell diagram. But as you can see, we do obtain the greatest amount of information about the mechanics of the respiratory system, and we can draw the greatest number of inferences about the respiratory mechanics when we do so with the Campbell diagram. But again, that is by far the most complex. So there are these various methods that can compute the work of breathing, and we were certainly interested in how frequently each of these methods appeared in the existing literature. So the goal of our systematic review, the kind of underlying motivation for why we even wanted to embark on this systematic review journey, really is a bit of a philosophical approach to science that Troy and I share with one another, as well as sharing with Dr. Campbell, the so-called creator, if you will, of the Campbell diagram. And he had a famous quote that said, "The tendency to foster a priesthood of respiratory physiologists is to be deprecated." In essence, what this means is that there has been a historical tendency for the few to sort of hoard the knowledge and keep it away from the many, which is not technically in the sort of vein of science, if you will. We believe the information should be freely available to many, many people, and be accessible to many, many people, so that everybody has the opportunity to have that knowledge and to use those tools available to everyone. And so we ultimately we are starting to work towards developing a what's the word I'm looking for? A standardized approach for measuring the work of breathing, a guidebook, if you will, for everybody interested in making this measurement. And this does not exist in any way, shape, or form in the current literature. So if one were interested in making this work of breathing measurement, you would have to kind of go into the literature and on a case-by-case basis, look at an individual study and try to glean what the best approach would be. And oftentimes there's varying amounts of information, varying different approaches that make that endeavor a very, very difficult one. And selfishly, Troy and I, when we were interested in this as students ourselves, had no resources on how to measure the work of breathing. We had no idea what we were doing. And so we're hoping to make it a little bit easier for those that are coming behind us. And we've created the International Respiratory Muscle Collaborative, or the IRMC, and feel free to follow us on Twitter. And with the approach, or with the hope of having this conversation and bringing in ideas from multiple people, and having a platform to really push all of the information that we've gathered out to as many people as possible. So the actual specifics of the goals of our systematic review, other than that kind of philosophical, what we hope to do to better the world that we're living in, is really, we want to learn about the quality of the methods used to measure the work of breathing. We really want to know which devices are being used, and specifically what type of pressure measurement device, what type of pressure transducers, flow measurements, so on and so forth. How frequently are each of these used? Are they discussing whether they're calibrated? So on and so forth. And then we also have an interest in identifying the frequency of the different work of breathing methods that are used. And we really want to know also what limitations the authors were discussing within their specific study as it pertains to the work of breathing. Even the Campbell diagram is not perfect and does not quantify all of the respiratory muscle work undertaken during, a breath or over the course of a minute. And so with that, I'm going to hand it off to Troy and let him tell us all a little bit more about our Sysrev experience and the results we have so far.
Thanks, JJ. Okay, so before I get started, I did want to give a shout out to my nephew. He was 9 years old earlier this month. Got him to send through his Roblox avatar and his Minecraft skins. So if you end up watching this, Noah, happy birthday. And also, before getting into the nitty-gritty as well, this is a big project, as you might come to appreciate in the coming slides, and it's not something that was just JJ and I. We had a lot of people working with us, including our colleagues Eli and Josh, and research students from NAU, Colin, Joe, my PhD student, Sarah, from the University of Sydney, and professional staff and collaborator, Jennifer Azortier, as well, from the University of Sydney too. So we couldn't have gotten this far without having a concerted effort from what's quite an international collaborative team. So the search strategy. So like the general idea that JJ put forward is we're basically just going to put all of the literature together and then see how often people measure flow with this device or pressure with that device, and what methods are used to quantify the work of breathing. So we need to somehow like capture that. And the best sources of information we thought we'd find that in PubMed, obviously, but then also getting onto Ovid and searching Embase and Medline. And I know that there is a little bit of a massive overlap actually between Medline and PubMed, but yeah, it's about 5% or less than 5%, but it's still a non-zero percentage of articles that are not covered in one, but are covered in the other. So we did do a little bit of redundancy there. The problem with that is that there's a lot of duplicates to remove, which we did as best as we could in EndNote, but we did come across that during our screening stage. To firstly identify potentially eligible papers, we used a combination of keywords that had synonyms surrounding the concepts, these three primary concepts. First, work of breathing itself. That might have been expressed as respiratory muscle work or pulmonary work, lung work, or power of breathing, respiratory muscle power, and so on. Exercise was one that was a very difficult keyword to try to hone into specifically what it was we were looking at, because as you can imagine, in the title and abstracts and any other text-based fields in the metadata of a record, saying the word exercise is quite it's a nebulous concept. We can say that this finding allowed us to exercise blah, blah, blah. Like we really needed to specify. So we not only just said exercise or exercising or whatever, we also had physical activity in there, cycling, rowing, running, walking, and a lot of different modes of exercise, at least to the extent that we could think of. But definitely this was one of the keywords that did blow out our search, our initial search results. Adults as well, we wanted to focus specifically just on exercise and work of breathing in adults. We only wanted original research articles so that we could get to the points of evidence in the literature where we had the highest chance of observing how measurements were taken, which is what you find with primary sources of evidence. We did not put a time limit on this. It's a fairly niche field. Although when we get to the preliminary results, you might be surprised how for a niche field, there is still quite a significant number of records that we were able to narrow down to or include. But we also know that there are some, particularly in respiratory mechanics, there is some knowledge which tends to get, I guess, lost over the years, or at least forgotten over the years, particularly from the 40s to 50s to nowadays. And it's almost like we rediscover that information on our own, only to realize that we sort of already knew that 20, 30 years ago. So to get everything since all creation, I think was important for us. And obviously, we wanted to make sure we could get a full text version of the article. But what was critical for us is that, well, number one, they needed to have measured esophageal pressure, because at least for us, we know of no other way of quantifying the work of breathing without measuring esophageal pressure taken as a proxy for pleural pressure. You could estimate it. You could maybe like loosely infer it from other physiological measurements, but that wasn't what this study was about. We were talking about the methods used to calculate it as directly as possible. So we really needed to screen out any articles that did not include a measurement of esophageal pressure. And then finally, if they didn't provide a true measure of the work of breathing, well, we wanted to identify, I'm talking about inclusion criteria, not exclusion. So we included only studies that did measure the work of breathing, which again was a little bit tricky, because in our field, a lot of investigators, including ourselves, we do like to not extrapolate the scope of our findings, but comment on the implications of our findings, which often would be a set of circumstantial observations made during an exercise bout, like how heavy you're breathing, how many breaths you take, what lung volumes you're breathing into. And we might say this has an impact on the work of breathing. So those articles would get flagged as potential candidates. And upon further inspection, like at the full text screening section, we'd realize actually no measurement of work of breathing is in here. We have to put it out. Exclusion criteria, we excluded non-English studies because we didn't have a good way of accurately, particularly in this niche field, of translating. And we did avoid and remove any secondary or tertiary sources of information, given that these were very unlikely to be enlightening for us for the primary question of how do these data get measured between laboratories. This is a Prisma flowchart for our latest search strategy. I guess I just want to flag that this is liable to change, because it's been some months since we ran the research strategy while we're drafting the paper. Once we get to the full draft of that paper, we'll then, do the updated strategy and then run with it. So these numbers are likely to change. But we started off with about 3,400 or so records obtained from the literature search. We then ended up removing some duplicate records, screening around 3,200 all over. We tried to get 288 full text articles, but could only get 286. So that's a pretty good throughput. And after this stage 2 screening of the full text, after removing articles that, it turns out didn't even have exercise in there, or maybe there was a literature review that snuck in and it shouldn't have. After doing that, we ended up on 116 articles included, at least in this preliminary data analysis for the findings that I'll show you. So just keep that in mind, that this is going to change by the time we hit publication, but it is still a good overview. Now onto data extraction, which JJ and if any of our teammates are watching, I can see that Eli is here and Jennifer is here. That was probably the most laborious of our processes for good reason, and I'll show you that soon. But as we did go through this process of data extraction, what we wanted to do was to capture, of all literature, what type of studies or who was being studied in this work of breathing during exercise literature? Was it mainly in, COPD patients or pulmonary disease patients, or was it just trained individuals? Where does the majority of knowledge lie when we think of the work of breathing during exercise? And also, what types of exercise? Is it running, swimming, walking, cycling? What's the most popular? Because only through quantifying that do we really get a good understanding for where the basis, the foundations of our knowledge exists, and where we might be able to improve it or expand upon it in underrepresented areas. So we thought that was important to capture as we went through. As JJ mentioned earlier on, we were really interested in not just the work of breathing, but the tools used to measure the work of breathing, down to specific things like what technology was used to measure flow during exercise, flow coming in and out of the mouth, what technology was used to measure pressure. And that's not just, esophageal pressure. There is mouth pressure, the pressure inside of the mouthpiece as well. What technology was used? What type of sensors were used? But I guess folding back to the overarching theme of our study as well, we did want to assess somehow methodological quality. So what was the quality of how these tools, how these assessment and analytical procedures were implemented in each study? And sure, in a lot of clinical trials, research, you've got very standardized, well-established, like risk of bias tools and quality and critical appraisal tools that help you say, oh yeah, this study gets 5 stars or it's an A+. In the work of breathing field, there is no quality assessment tools, so we sort of came up with our own. And by and large, what that meant was that we thought, okay, what are some questions we want answered that help us determine whether or not by reading a specific article, there is enough information here for me as a novice researcher, going back to the days when we knew little of this topic. Is there enough information to get started? What are the important things I would need to see in a paper to start to reproduce that technique in my own lab? And we asked those questions throughout all of the data extraction procedure of the systematic review. But when we're talking about measurement devices, some of those important questions were not only what type of devices, so that we just know what brands we have to look for, or what's the most popular technology, but then also too, is there any description provided in the paper on how or if at all the devices were calibrated? JJ spoke earlier about a device needing to faithfully measure rapid changes in pressure and flow rates during exercise, because they can oscillate quite frequently. And the way that you measure the adequacy of a device to do that is using by assessing its frequency response. It's an engineering term, and all that really means is that up to a certain frequency, the signal doesn't get distorted. And you want a good frequency response on your devices. And so we were searching for papers that would report on the frequency response so that, we could assess whether or not those devices were adequate. And then sometimes, as we've, investigated in the past, is that even if you do have a device that's not adequate with its frequency response, it might be a bit sluggish, it might distort the signal. There are some software or algorithmic approaches you can implement to undistort that signal. And so we wanted to capture how many times studies cited those compensation techniques, dynamic compensation. And that starts to get us into that realm of assessing the quality of the methods of this literature. Obviously, moving on, we wanted to look more hard or more focused at what type of catheter was used. There's various types, how they were positioned, because that's something that, again, learning this technique, you need to know where in the esophagus how do you put it in the esophagus? What sort of tips and tricks do you use to make sure it's in the right spot? Is it validated when you get to the right spot? How do you know? So it's all of that sort of stuff we were assessing along the way. And then finally, we captured a range of information, which I won't present all of it today, but mainly the important things on the work of breathing, how it was determined. Answering some of the questions JJ had posed earlier. Well, what are the most frequent methods used in the literature? How were pressure and volume data processed? And were the units reported correctly? Because as JJ had mentioned, like it is a bit of a misnomer, but it's a historical misnomer. So it has been propagated through the decades that when someone calls the work of breathing, what they're actually really meaning is a measure of power of breathing, because that's typically the units that have been cited in literature as joules per minute, which is really a mechanical power. In the field of exercise physiology, when someone exercises on a bike and we measure physiological responses, we don't typically peg those physiological responses to the amount of work performed on a bike in joules or work performed on a treadmill. We look at the work rate, because the rate at which you perform work dictates the intensity of that exercise and the magnitude of your physiological responses, not the work that you perform in that bout of exercise. There are very different insights that you can gain from work and power. And this is fundamental to exercise physiology, yet hasn't creeped over yet into respiratory mechanics. So we wanted to see how frequently this misusage of the term was in the literature. So getting on to now how big this project was for us. This is our first formal endeavor into systematic reviews. We saw, plenty of different software packages out there to kind of help manage the process. And we ended up on Sysrev, being open source, being a nice, sleek design. Once we got into it, we figured that the best way to proceed with it was to actually split this Sysrev project up into 3 separate existing projects on Sysrev. The first one would be dedicated to title and abstract screening. The second one would be the full text screening stage. And then finally, data extraction. And it's this stage which, as you can imagine, took the longest. Because if anyone is familiar with the back-end platform of Sysrev, you've got your labels that you can define, different types, different limitations on what can be input in there. And as an example, we had approximately 50 odd labels, I think, or 49 labels, where each individual reviewing those records of the team to a record. We had a lot of opportunities to have disagreements. Not disagreements because we didn't say the same thing. It's just we might have typed in the free text entries the same thing, but with capitals instead of lowercase characters. And so that comes up as a conflict. So what it did mean is we spent a lot of time then resolving those conflicts. So if you do end up going onto our Sysrev projects and you see we've got a lot of conflicts, it's not because we hate each other and we had massive arguments. It's just because we might have nuances with how we spell esophageal with the UK versus the US spelling. But nonetheless, it took quite a while, but we got there. So now we've got to talk about the results. I have the 3 asterisks here, qualifying that these are likely to change, but the general story will be the same. And look, if you're at this point in time not exactly following on with what worker breathing is or why it's important, that's okay. What's more so important over the next series of slides is to see what I want to try and do is build an appreciation for when something is being reported consistently and perhaps when something is not being reported at all. Because when something is not being reported in a methodological section of a paper, we have to assume that it was either not done or that, we can't assume that it wasn't done. We just don't know. So we have to say, it was unclear. And with that lack of clarity, lack of transparency, how are we able to teach the investigators coming behind us or those wanting to get into this field how to do this measurement well? So let's start off from the top, going through in a very similar fashion to the flowchart I showed you earlier about data extraction. The study populations. Who do we have the most information on? On the left set of panels, I've got the number of participants, so the N sample size for each study, whereas I have the number of studies that we included, which was 116 and 1,649 respectively. They're basically the same fractions, but I did want to express it as a percentage of all participants, just in case there was one study, but a lot of participants. That still biases the weight of knowledge towards that mode, that population. So The thing to draw, I guess, your focus on too is your sort of top 3 contenders for the populations of people that were examined in the literature. Healthy subjects win out. So we have a lot, if not, the majority or even 2/3 of all studies are on healthy subjects in the work of breathing. And there's a lot of reasons for that, I guess, over the years. It's, where you usually start with understanding new aspects of physiology. And there was an explosion of respiratory mechanics around World War II, done on healthy individuals, but we came to appreciate that we, need to focus on lung disease. So about a quarter of the weight of evidence of mechanics, work of breathing during exercises on lung disease, pulmonary disease patients, and then also a fairly non-trivial fraction dedicated to looking at it in the elite athletic population as well. Not so much, but, rising interest in persons with obesity and cardiovascular disease, which our group has significantly contributed to. But definitely we're looking at the healthy so the main knowledge structure here lies with the healthy population. Exercise, we have a clear winner, cycling. The most common way that we assess the work of breathing during exercise is cycling. And that's possibly due to the fact that, the peripheral devices that you use to measure the work of breathing are not very amenable to swimming. They're not very amenable to rowing. It has been done, but there are physical constraints, logistical constraints associated with it. Cycling is the easiest. Stationary cycling on a stationary bike where you can be guaranteed within rough approximation of where someone's head is going to be almost all the time. So you can put devices near the head without that head bobbing and moving around or ducking underwater. They're on a bike. They're not going anywhere. So that's the most common mode of exercise. When we look to how flow and pressure were measured, what were the most frequently or most popular devices? Flow, the pneumatachograph, it is a type of technology that measures flow using differences in pressure across a small resistive element. They are, as far as technology goes in this field, then they're pretty simple, pretty straightforward, pretty cheap relative to the other devices that are on the list. I won't go through them in detail, but there are a number of ways that people have measured flow, but the most popular is the pneumatachograph. Pressure sensors, it's a little less clear. Obviously, we have the variable reluctance pressure sensor. For those in the field, you might recognize these as Valadyne pressure sensors. They do make up just over half of all studies or number of devices that were used in the literature. But then we have some others here, piezoelectric resistive, making up about 20%. These are the things that you might find in medical devices and also, the automotive industry as well, maybe in aeronautics as well. It's a very common and relatively cheap type of pressure sensor. We use it quite a lot. But then at about 16%, we don't know. We don't know. And about 16% of all devices used in the literature, in this literature, we just could not find out any mention in that paper to what type of pressure sensor was used, just that they used a pressure sensor. So now we're starting to get into this idea of lack of transparency. We also had a small fraction here of unknown. This is a little bit different to not reported. Unknown is when back in the 1940s, someone says they used this method, or rather this manufacturer for their pressure sensor, and there is no record on Google of what type of technology that pressure sensor is. So to the best of our ability, they might have cited what device they use, but we can't reverse engineer, if you will, what type of technology that was. When we talk now about more so the quality, or at least the reporting quality in the paper on these pressure sensors and flow sensors, we have those 3 questions that we ask. We ask, okay, did you say anything about calibrating the device? Anything at all? It's good practice to calibrate. We shouldn't just assume that you do. It would be nice to have a statement to that effect, and if possible, describe potentially how or what standards you use to calibrate those devices. We see that in our studies, or this here on the x-axis is number of devices. I didn't choose number of studies here as the denominator. in these fractions because some studies did use 2 different devices. And so there will be more devices in this literature than the number of studies. So we expressed it as a number of devices. So of all devices that were reported in this literature search, about 65% did not say anything about calibration. And 100% said nothing of the frequency response. And if that frequency response was poor, did they compensate for it? There could be a number of reasons for this. The most likely one is that flow sensors, typically the pneumotachographs that are manufactured and commercially available, generally there's an understanding, I guess, that their frequency response is adequate. And so I think we don't feel compelled to report on it. But I think where it is more important and less observed is the impact of frequency responses, calibration, compensation on our pressure sensors. So let's have a look at the pressure sensors now. So about the same proportion of studies failed to say anything about their sensors being calibrated. So we can't assume that they were. We have to assume they might not have been. The frequency response was only reported in I think this is 1 study, and compensation for a poor one as well, maybe in 2 studies here. So the majority of people, investigators, when we're publishing our studies, we're not commenting on quite an important concept, how adequate our tools are to measure the signals that we expect to see during exercise. Those are our, bread and butter tools, pressure and flow sensors. Then we turn our attention to catheters. What catheters we used to measure esophageal pressure? The 3 main types here, categories here, are balloon-tipped catheters, which I'll show you in just a moment. We also have a few that said nothing of what type of catheter they use, but it's not the majority. So this is good. This is a good fraction. Only 3.4% of all studies said that. And 1 study used a nifty microtransducer on the end of a catheter. But clearly, our balloon-tipped catheter is the most popular. That looks like this. It's a catheter, as JJ mentioned, gets inserted via the nose, sits in your esophagus. You can see that it has a balloon on the end of it, the balloon tip, which needs to be inflated with a small amount of air to work properly. And also, when it's in the right section, you tape everything up. You need to connect it to your devices. Sometimes those devices aren't close by. You may need some extension tubing. And some of the research that we've done has illustrated that as soon as you add some extension tubing onto these devices, they become progressively worse and worse and worse in their ability to not distort or to prevent distorting of the signals during exercise. So you want to keep that distance short. So we need to know how many papers actually reported on how much air was injected and also how often was extension tubing used. And to that end, about 2/3 did not report how much air, or if air was injected at all, into these catheters. And the majority, an overwhelming majority, did not make any mention of extension tubing. Now, that's not to say that there was no extension tubing used. It's just, we just don't know. It's important, I feel it's important to state that no extension tubing was used, as much as it is to be clear on when it is used, because that gives me the ability to evaluate, was the pressure catheter used at all compromised by potentially a poor frequency response by the addition of extension tubing, therefore skewing your results a bit. When we think of how this catheter gets put into the esophagus in the right position, there was a plethora of different ways that people could describe it. And this is quite important for trying to build in a new lab or a new investigator taking on this technique. How do I put it in the place I need to put it in? You can see there's, a fairly, not even distribution, but a stacked distribution. The most common usage or most common descriptor found in text was a vague statement saying we put it in the lower third or lower 2/3 of the esophagus, which is, okay, sure. I know what part of the body I'm inserting it to, but it's still very vague. There's no step-by-step instructions on how to do that. And then we go all the way down to, here, not very popular, but is done sometimes. Some catheters have EMG electrodes on them as well. And so some people position it according to the EMG, not the best place for esophageal pressure. But really, what I want you to take away from this slide is two things. The descriptors that specifically refer to validating the position. That's the occlusion test and the constant transpulmonary method. Validation, all that means is that this is an extra step that you can do to make sure the balloon is in the right place to effectively serve as a replacement for measuring pleural pressure. If it's not validated, then you're not terribly sure that the measurements you're getting are reflective of changes in pleural pressure. And so what good is esophageal pressure if you can't validate that it is a good proxy for pleural pressure? Only about 40%, just under 40%, used verbal written descriptors that indicated position was validated, which isn't a lot. That indicates that approximately 60% did not, or we have to assume may not have validated the position of the catheter. And another important metric here is that about 20%, 23% didn't actually say anything at all about how they position the catheter. So if you're trying to learn this field, to get involved and look at studies, to gather information on how to position a balloon catheter, about 1 in every 5 or 1 in every 4 papers won't have that information for you. This is my last slide, so if you're still here, thank you very much. The biggest sort of question that we have answered is, what is the most common way of measuring the work of breathing? So of those 4 pressure volume loops that JJ had put up, there are more than those measurements methods out there, but the primary ones were the 4. Of those 4 most popular methods, which was overall the most frequent in the literature, we have the work of breathing methods up here. We have pressure volume integration, the simplest measure of work of breathing. That was by far the most popular measurement of all of the studies in our literature. The headstrand and modified Campbell diagrams came in an equal second place, and the other ones not so much. So the modified Campbell diagram, the one that provides the most amount of information, it came in second. It's not exactly a close second, but it's still, on in the top 2, tied for second place. When we make these measurements, though, before you actually get your joules or joules per minute for power measurements, you've got to process this data, this pressure volume data, and that's another critical thing for someone learning the field. You can take many breaths and average those breaths together to get a representative ensemble averaged loop. Or you can calculate the work of breathing breath by breath by breath by breath, and then average those individual values. Might not sound like much to you on which way to do it. And in reality, we don't know which way is better. But really the important thing from this figure is that 36% didn't mention it at all, how they treated the data to construct these loops to compute work of breathing. So a third of all papers don't describe how they get to that point. Another point here is that, okay, when you do decide that you want to get a measure of work of breathing, what time ranges, what sort of ranges of your data are you measuring work of breathing over? The majority of individuals would say at a specific time point, we got 8 to 10 or 8 to 20 representative breaths. So that was based on a number of breaths that would go into the average. Others would use a specific window of time. So, if 12 breaths occurred within 30 seconds, it would be 12 breaths. Some people used a range of ventilation. So when ventilation was about 50 liters per minute, all breaths that were about that ventilation, average them together. Again, about a third didn't mention at all how their pressure volume data went into providing their values for work of breathing. And just quickly, but not any less importantly, the work of breathing, 70% of the time was misrepresented in units of power of breathing. So you have 70% of the literature using joules per minute as the incorrect definition of work of breathing here. which is quite a significant thing to get wrong. And this isn't really a thing about getting wrong, because if everybody in the literature interprets it that way, you might say no harm, no foul, right? Like if everybody knows that. But there's no standardization between integrated areas of knowledge then, between exercise physiology and respiratory mechanics. And it's that nexus that JJ and I are really interested in. And so we do want to try and homogenize that to make that terminology interchangeable between the two disciplines so that we can generate better insights. I do have also whether or not limitations specifically to the work of breathing measurements were discussed. And you can see here that, again, 2/3 said nothing about how limited their measurements of the work of breathing were. And even though you could do the Campbell method, which was the most informative, there are still limitations there. And to not acknowledge them, I think, is a lack of transparency that without that acknowledgement, the reader, particularly the naive reader to the field, isn't equipped with enough information to critically evaluate your interpretations of the data. So that's a really important thing. I do want to just highlight that, in our publication, when we get it out there, we are going to do some content analysis of the actual limitations that people wrote in their discussion section, so that we will try and identify common themes and see if they change according to different work of breathing. We just don't have that data ready yet, but it's coming. So to summarize, look, there's a lot of text here, so I'll quickly focus on one and then the other. The most common things, we said healthy populations were the most studied. Cycling on a bike was the most common exercise mode. Flow was measured with the pneumatachograph most commonly, and pressure using a variable reluctance transducer, or the Validine, probably coming as no surprise to people in the area. Balloon tip catheters, again, most common. The majority of studies use them to measure esophageal pressure, and pressure volume integration was the most common method, which is interesting because it's the least informative method as well. So the most commonly used approach is the least informative in the field of mechanics of breathing during exercise. The not so good things are pretty much everything I was emphasizing as we went through. Hardly anyone mentioned if their devices were calibrated, what the frequency response was, and whether dynamic compensation was applied. There's a lack of transparency about what people do with the esophageal balloon catheters. How much air they inflate it to? Do they use extension tubing or not? And how was it positioned? And was it even validated? We see that there's a lot of, I wouldn't say lack of transparency, and I don't want to sow the seeds of suspicion of like the field in general. We just don't like telling you the truth. That's not really what I mean. I think we do this without realizing how difficult it is then for other investigators to reproduce these types of studies. And that's something that this data will hopefully put in front of our faces and cause a shift in the literature to try and address. About a third did not explain how pressure volume data were processed, and the majority did not report the correct units or even discuss limitations of their work of breathing measurements. So where do we go from here then? If we're saying that's a general lack of transparency, what do we do? Well, in a follow-up study, what JJ and I have constructed was an online survey that we've run. It's still open, so if anyone is interested in participating in it, please let us know, where we sent out an online survey to professors in the field, early career investigators, and students that might be involved in understanding and learning about the work of breathing, asking them on their own perceptions of barriers to learning this technique, or the information that's out there. Where did they get it from? Do they want to see more standardization in these methods as well? So we're sort of following up from this systematic review what the people want, what the people in the field would like to see, with the longer term view that perhaps we can start to establish some standardized guidelines. A point of reference, something where people can go to start to make these measurements in their own lab, because they are pretty informative measurements. It's a unique tool to use, and you gain some incredible insights into lung and chest wall physiology if you do them right, which is probably the critical thing here, is to do them with enough accuracy and enough scientific rigor that the inferences you get from these measurements are as valid as they can be in this mostly objective world of science that we live in. So that's what we've got planned next. And I guess what I'd like to do now is acknowledge the rest of the team. Again, for people working on the systematic review, the co-founders, JJ and Brian Taylor of the IRMC, from which these, the motivations for these projects were largely born, our online survey working group, which is now expanded. I should include some more people under here, and our mentors over the years. Bill Shield, Bruce Johnson, Ken Beck, Andy Lovering, Norm Morris, and Surendran Sabapathy. So thank you to them, and thank you to everybody who stuck around this long. We really appreciate that.
It's so cool to see this because, it's over a year and a half ago that this project popped up that had 50 labels. And we had never seen someone else attempt that. We had tried it, but, to see someone else truly undertake, it was very impressive. And so we've been looking forward to this for quite some time. Real quickly, for those of you in the audience, we're going to have a quick Q&A session after this with our founder, Dr. Tom Luchtefeld. So stick around. That won't take too long. We'll be back in about 5 seconds.